Welcome to our presentation on modeling diffusion. So the initial research question that we answered in this experiment is, does the mass of a particle affect its rate of diffusion? And we hypothesized that larger objects have slower velocities than smaller objects because the larger surface area leads to an increased amount of collisions with water particles when applied the same force. And in this scenario, our larger particle was 2.5 times larger than our smaller particle, and the average velocity of the large particle was 1.2 micrometers per second, and the average velocity of the small particle was 4.77 micrometers per second.
So for our model of diffusion, in this model, force is applied to a particle in which it causes it to move in a certain direction. In our experiment, which is similar to this model above, we studied how an object's mass affects velocity, its rate of diffusion. So if we look at the diagram above, we have two separate gases diverted by a stopcock. By removing the stopcock, the gases can diffuse naturally, and it's reflected in model C.
So for experimental design, we wanted to measure the size of the bead using the diameter and the position of the bead over time. We then found velocity of both the 2 micrometer and 5 micrometer bead while in H2O at 20x magnification. We used the same procedure for both beads separately and recorded, then used tracker to find the position to determine velocity. The errors is that we could have bumped the table, and we also could have dropped one of the beads at a higher height, which would then, of course, make them move faster. So we needed to keep those consistent. We found our results that the average velocity of the large bead was much slower than the average velocity of the small bead. So this allows us to conclude that a higher mass will result in a slower velocity as long as consistent force has been applied in a system with a concordant number of water particles in which to potentially collide with.
And so we were talking about how we would describe the motion of beads in the solution and if it matched our expectations. So we predicted that the beads would disperse randomly and spread out in an even-like fashion. However, we actually demonstrated that the motion was like waves. There was net displacement overall. However, it took longer to occur and the particles swept back and forth, so it took longer. And comparing it to the computational situation, and what the particles represent, we thought they'd represent ligands floating around solutions, and the water in our model represents actual water and or plasma. Going back to 3D diffusion, we can look to the right and see our 3D representations of the particles in the solution.
There were several comparisons to be drawn between our model and the computational model. The similarities are that we were able to change the mass in both our model and the computational model to determine the difference in their velocity or their rate in diffusion. And then we were able to track particle position, whereas it was tracker or an actual trail that the particle left behind. Differences included, of course, human error, imperfect elastic collisions. Our model, of course, was not confined within a defined space, and our beads eventually settled, whereas the computation model never lost their velocity.
So in our experiment, with a fixed amount of kinetic energy, we noticed as mass increases, the velocity will decrease and vice versa. And yes, we noticed that the larger beads moved with a slower velocity and the smaller beads moved with a faster velocity. And that is representative of the kinetic energy equation and the momentum equation, which proves them. And finally, another factor to consider is the reactivity of the solute in terms of its interaction with the solution. It wasn't addressed in the model versus the experiment, and the two substances might have had a polar relationship which caused the diffusion, but in contrast, our model did not have a polar relationship between the solute, which was the beads, and the solution it existed in.